Hello, everyone. Okay, right. So a slight change of plan. I was planning to go through differentiation today, but I've managed to get a guest speaker for next week. So next week we have a guest speaker talking about differentiation. So I will continue going through Newton's laws today. I'm going to talk about friction, and once again, I'm going to go slightly more on the easier side today. So compared to my normal webinars, which you can find recordings of, they're all available. So if you want the harder stuff, please watch my last year's webinars. And this year I decided to go slightly on the easier side. Okay, so last week we finished here, and I'll share my screen. Share my screen. You should be able to see my screen, and I should be able to see the chat. Yes, I can see the chat. Okay, excellent. So first, I want to talk about friction force, and I've shown you the experiment. The experiment last week. Well, not the experiment-ish with the boxes. So should I go through the experiment again, or you do remember? So type yes if you'd like me to go through again. Okay. So the setup for the experiment is as follows. We have a box. So we're talking about what friction force is and what do you do with the friction force. And you push the box with a force F, applied force. Push the box with a force F applied. And the question is, what is the friction force? So there's a friction force here, of course. There's a friction force here, and it has a direction to the left. It's trying to prevent the box from sliding. Friction force. Force of friction. And we are interested in how does the friction force change with the applied force. Well, it's quite straightforward. If the box is not moving, they have to be exactly equal to each other. If the box is moving, is not moving, box not moving, not moving, that means F applied is exactly equal to F friction. And let's verify this. And let's say we want to move a fridge. And we okay. So when we start pushing the fridge, you can see that the applied force is 1 Newton and the friction force is exactly 1 Newton. Because the fridge is not moving, because if one of these forces was bigger, the fridge would be moving in that direction. So I keep increasing the force. And if I increase the applied force, the friction increases as a result. Yeah, so the ground tries harder not to allow the fridge to move. Okay, there's more tension in the ground. There's an electromagnetic force in the ground, to be frank. It's the electrons in the fridge pushing against the electrons in the ground, and there is an electrostatic repulsion force. So let's talk about this just for a quick second. So how does friction occur? Right. So if you zoom in to this, try to make it fancy, you will see the surface of the fridge is actually quite rough. So this is the fridge. And this is the ground. I hope that makes sense. So this is the ground and this is the fridge. And if you zoom in, you will see that these edges, they touch each other. These edges, they touch each other. So there's a contact force here between the fridge and the ground. There's a contact force which pushes the fridge that way. And here, another force pushes the fridge that way. So technically, there's a normal reaction force from the ground, and there's friction. And sometimes we say that friction is a horizontal component of the normal reaction force, because it kind of makes sense. Friction is a horizontal component of the normal reaction force because friction is a reaction from the ground. So yeah, so you can see all forces, all sorts of forces. And out of these forces, the resultant force, you could say that the resultant force is that way. Or you can say there are two forces. There's an upwards force, the normal reaction force, and there's the friction force. Okay. Now, this is the nature of the force, of the friction force. And also, I think I've mentioned this before, that this is an electromagnetic force. This is due to the electrons in the fridge repelling the electrons in the ground. Okay, because when they get close together, the atoms are negative on the outside because they have the electron cloud on the outside, and the ground is made of atoms which has electrons on the outside. So the electron cloud of the fridge and the electron cloud of the ground, they interact and they repel because they're both negative. Okay. So when the box is not moving, the applied force is equal to the friction. So let's have a look. So I'm pushing with 54, the friction is 54. I increase the force, 104 and 104. 154 and 154. Well, it's going to start moving at some point. 204, 215. So as you can see, up to a certain value, if we were to draw a graph, we would see that the friction force is exactly equal to the normal reaction force. The friction force is exactly equal to the applied force. So this is the F applied. And this is the force of friction. So if this is 50, this is 50. If this is 100, 100, 200, 200. But at some point, 250, 250, How do you calculate how high a flow has to be to the box start moving? That's a good question. I will show you. I haven't tried the fridge yet. I also did it with the box. Oh, wow. Has to move at some point. The maximum force is 500. Okay, not enough force. So we have to reduce the friction. Okay, so let's reduce the friction. 350. 315. Okay, 400 and okay. And 74, 400. So it looks like 475. So what happens at 475? So let's assume it's 475. I can't catch the moment when it starts moving. Let's say the maximum force is 475. When 475, the friction force, the box starts moving, and immediately the friction force drops to 354. Okay, so let's just trace this back. Stop, 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 stop. You have two different friction forces when it's sliding and when it's not sliding, and these are different. Okay, so 370, 426, 456, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73. Okay. You all notice what happened. When it reaches 473, 473, the friction force immediately drops to 354. So it drops to 354. And then this is 473. This is 354. And then the friction force doesn't change. No matter what you do with the force, no matter how you increase the force, the friction force does not change. Look, I can increase the force further, and it's still the same. I can reduce the force. So while it is sliding, it's going to be the same friction force. So we have two different friction forces. The friction force when the static friction and the dynamic friction. So this is maximum static friction. Maximum static friction. And this is dynamic friction. Dynamic friction is always the same, and static friction is like this. So static friction, the formula, static friction, force static, is less than or equal to the coefficient of static friction, mu s, multiplied by the normal reaction force. So the friction depends on two things, on the roughness on the surface, which is mu, and the normal reaction force, which is n, well, mg. In normal conditions, it's mg. So it's usually mu mg, mu s mg. And dynamic is exactly equal to the coefficient of dynamic friction times n. Right. Neil, your question. So Archie, how do you calculate how high applied force? It has to be greater than mu s. So for example, if you have a mass of 100 kilograms and the coefficient of static friction is 0.4, then mu s mg is going to be 0.4 times m, which is 100, times g, which is 10 for simplicity. So it's going to be, what, 400? 400 newtons is the minimum force that you need. Okay. Does that answer your question, Archie? Okay. Raghav, why does the friction force drop so abruptly rather than gradually? Well, because we're still pushing. We still it kind of breaks the like usually what happens is the sharp edges they literally break down when you start when you push, and these corners they break, so they give way. It's like breaking a ruler. It's bam 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 bam. You don't ask why the force in the ruler changes to 0. Once it breaks, it's immediately 0. Okay. Neil, I'm currently reading an explanation for the laws of friction. I'm slightly confused with one particular. Frictional forces are independent of the area of contact between the surfaces. Given that the turning a body and reducing the area of contact. Now, Neil, true. I have been thinking about this question for a very long time. Okay. Why have I been thinking about this? Because when we learn about friction, the friction is either mu s times n if you're not sliding, or it's mu d times n. So it does not depend on the area. It only depends on the friction force, on the coefficient of friction and the normal reaction force. So it looks as if the friction absolutely does not depend on what the contact area is. It only depends on the materials that it is made of. That is the theory. But mu, so to summarize, let's quick summary. First, friction depends on first, sliding or not, sliding or stationary, sliding or stationary. 2, materials and smoothness. And 3, the contact force. So it does not depend on area. Okay, the friction does not depend on the area. So presumably, let's think about cars. 2 cars, one with very big wheels and one with small wheels. They should have the same friction force because because it doesn't depend on the contact area. And yet, we know that in racing cars, they use sleek tires. So they maximize the contact area. And this question has been bothering me for quite a long time. So Neil, you're not alone. It bothers me as well. Like, well, it looks to me as if the coefficient of friction changes with a bigger contact area. So the coefficient of friction is a very complex thing. We use a simplified model where we say, oh, the coefficient of friction is the same. Well, apparently it's not the same for a sleek tire and for a for a wide tire, for a narrow tire. Apparently, the coefficient of friction is different. Presumably because there are more forces, there are more complicated forces between the molecules, between the rubber. There's also the factor that the rubber warms up when the car goes. So lots and lots of things. So let's say in the models that we use, it absolutely does not depend on the area. At least it does not depend on area in any predictable way. Okay. So yeah, I mean, if you think about metal on ice, okay. Yeah, if you think about metal on ice, if you use a large surface area, you put a piece of metal on ice, it will slide very easily. But if you have some spikes, it's very small contact area, and yet you will have much more friction with small contact area. So it's very unobvious, and the opposite is true for racing cars. Big tires means more friction. Small contact area means less friction. So yeah, it's we use a model which is a simplification. So for all intended purposes, always assume that the friction force does not depend on area. I hope that makes some sort of sense. Another friction, why is air resistance proportional to velocity but friction is not? Air resistance is not only proportional to velocity, it's at high speeds, it's proportional to velocity squared. So there's a more complicated relationship between air resistance and speed. With this, it's quite obvious because you have a larger mass of air that you need to get out of the way. So an object moving through the air transfers its energy to the kinetic energy of the air. And the kinetic energy is proportional to velocity squared. So the faster you move, the faster you need to move air out of the way. So it has to be proportional to V, because it's to do with the energy transferred. Here, it's not the case. You're transferring it into heat, and you are with more speed. You do more work against the friction per second, and that corresponds proportionally to the amount of energy being lost. So, yeah, why does it not depend on speed? Well, actually, if you think about it, think of a good example is water skis. The faster you go, the less friction there is. Okay, but if you're on if you're on a like on water skis, the slower you go, the more friction there is, and the faster you are, like you lift above the ground. So technically, you're skipping over these bumps on the ground. If you're moving fast, friction tends to be smaller. Yes, coefficient of friction is usually given to you, or they ask you to find the coefficient of friction. The more I was thinking along the lines of boundary between static and dynamic friction into the gaps, yeah, you can think of static friction. You need to you have set on into the gaps, and when you move, when you push, it jumps out of the gaps, so the friction is smaller. If you try to move a heavy fridge or anything heavy, you will notice that it is harder to get it moving rather than to keep it moving. So dynamic friction tends to be smaller than static friction. Dynamic friction, so I'll write it down. Dynamic friction. Dynamic friction tends to be smaller than the maximum static friction. Okay. Example. Harder to get a heavy bridge moving rather than to keep it moving. Like indoor biking, harder to get the wheel moving rather than probably. I'm not sure. Indoor biking, not sure what. Yeah. Neil, yes, I see what you mean. You don't have much time to settle into the gaps, into the dimples. How would the dynamic friction be larger than the static friction even work? How would the dynamic friction be larger than the static friction? Well, I'm thinking about liquids. It might be true for liquids on non-Newtonian fluids, for example. That would definitely be the case, because the faster you go, the more resistance there is. Okay. Similar to dragging a ruler across a piano. That's an interesting example. Why ruler across a piano? I guess that makes sense. Okay. All right. Sorry. I'll keep moving. Otherwise, yeah. So let's just look one more thing. So once more, if when I'm pushing and it's accelerating, yeah, you see the speed is increasing because the applied force is greater. But I don't need to push that hard anymore. Once I got the fridge to move, I can reduce the force to 354, and the fridge will keep moving with a constant velocity. Yeah, so you need a bigger force to get it moving, and then you can push with a lower force to allow it to move with constant speed. Right. So that's friction for you, and it's a very interesting force. Now, another thing that we're going to use a more simplified model for friction. A simpler model for friction is simply when the coefficient of static friction is equal to the coefficient of dynamic friction. And that means that the static is always less than or equal to F dynamic. Yeah, so here I just wanted to mention, so this value is mu Sn, normal coefficient of static friction times the normal reaction force. This force is mu Sn as well, and this force is mu Dn. And as you can see, it keeps the same. Does the greater applied friction force come from where one has to apply a greater force to accelerate the object? It's not because of that, no. It's just the friction. Look, let's take a box. The applied force is 79. So you keep increasing the force. So 119, it starts to move and it starts accelerating. Look, accelerating. All I need to do now is to reduce the force to 89, and it will keep moving at constant speed. So the speed only depends on how quickly I reduce my force to the minimum value. So if I keep pushing with 119, it will keep accelerating. But I don't need to move at that speed. So once it starts to move, I can relax a little bit. So I reduce my force to 89 and it keeps moving at constant velocity. And then there's a whole lot of things. I mean, you can't keep accelerating the box. You can't move the box at 20 meters per second. Yeah, there are other things involved in there. You have to move your body, and a person cannot move their body at 20 meters per second. Okay, so a simpler model for friction is when and the graph becomes this. Okay, so this is force applied. and this is the force of friction. And it will just go like this. Easy. So this value is mu n, because mu is the coefficient of friction. So in most cases, in most problems that we give you, the coefficient of static friction and coefficient of dynamic friction is the same, and we just use mu for it. So basically, okay, let's look at 3 examples. Let's say the box is 7 kilograms, 7 kilograms, 7 kilograms. So example. And the coefficient of friction, mu, is, let's say, 0.3. In the first case, I push the box at 15 newtons. In the second case, I push the box with 21 newtons. And in the third case, I push the box with 30 newtons of force. What happens with the box in each of the cases? Well, first of all, we need to calculate the maximum friction force. Is equal to mu times n, which is mu mg, which is, well, g is 10, come on. Mu mg, which is 21 newtons. So what is the friction force? So in this case, the friction force is going to be exactly 15. Exactly 15 newtons, because we haven't exceeded the maximum friction force. So the friction force will increase until maximum friction force is reached. So 15 is 15. So force of friction is 15 newtons, and there's no movement. No movement. Now here we have reached the maximum friction force. So the friction force is going to be 21 Newton. But in this case, the friction force is 21 newtons, and it's stationary or constant speed. Okay, here, even though the forces are equal, you cannot have constant speed because it cannot be moving, because dynamic friction is exactly 21 Newton. So if it's less than 21, then it's stationary, it's static. Yes, normal reaction force. So when you talk about a box box on the ground, there's the normal reaction force and the normal reaction force and the mg. Mg and normal reaction force. So N is equal to mg. If the box is not going up or down, N equals mg. This is a typical scenario. Typically, this is true. Now here, the force of friction. Now we have exceeded the maximum friction force. So the friction force is 21 newtons. 21 newtons. Dynamic. And this could be dynamic or static. and this is static. So this depends on whether it was moving initially or not. If it was moving initially, then it's dynamic. If it wasn't moving, then it's static. Now, the friction force is 21, and the box is accelerating. The resultant force, there is a resultant force which is 9 newtons. So the acceleration of the box is the resultant force divided by the mass of the box, which is 9 divided by 7, which is 1.2 out of 7. 2/7. I used to remember that. Now I can't remember. So 9 over 7. 1.29. 1.29 meters per second squared. So the box is accelerating. Why is F static less than or equal to dynamic friction? No, maximum static force. So in maximum static force, the dynamic friction tends to be smaller than the maximum static friction. But static friction is only greater. So look, static friction is less than the dynamic friction here, and it's only bigger than at a very small section here where the static friction is greater than the dynamic friction. So this is static friction, and this is dynamic friction. So the static friction is typically less, but the maximum static friction is greater than dynamic friction. In the simplified model, static friction is always less than or equal than dynamic friction. Yeah, in the simple model, we ignore the small section. Exactly. We don't have the static friction is the maximum static is equal to dynamic. And this solves most problems. I mean, you don't need to worry too much about them. And usually the static friction and the dynamic friction has very similar coefficients. So yeah, you don't have to. Okay. Now, a common misconception about static force. Common misconception. Static friction force always acts in the opposite direction to motion. This means it is not true. Can somebody give me an example where the friction force acts in the same direction as motion? Very good. Archie, yes, a car. So this is a piece of paper, and if I put my calculator on the piece of paper and I pull the piece of paper, you can see that the calculator moves with it. So the friction force between the paper and the calculator causes the calculator to move forward. So the friction force is forward and the calculator is moving forward. So the friction force is that way and it's moving that way. So the friction force causes motion. This is something quite unusual because usually you're taught friction force resists motion. Well, not always. But then you would say, oh no, but that's only static friction. That's only static friction that causes the motion. When you have dynamic friction is always in the opposite direction. Well, it's not the case either because I can slide the paper quickly, and you'll still see the calculator move that way. See? This was dynamic friction, and it still caused the calculator to move that way. Okay? Do you understand what I was trying to say just now? Do you understand what I mean? Yeah, so the friction causes movement, and friction is in the same direction as movement. Okay. When I pull the paper from underneath this calculator, there's a friction force between the calculator and the paper. Now, when I move it slowly, it is static friction between them. It's static friction that causes the calculator to move that way. And the force of friction is that way, because the only force that's pushing the calculator is the friction force. But then the dynamic friction, it's the same thing. I just pull the paper faster, and you can still see that the calculator has shifted. Does that make sense, Rahul? Okay. We're gonna have an example. We're having a question on that. Yeah, in the frame of reference of the paper, yes, it resists motion. Of course, it resists sliding. But you just need to be very careful with the language that you use, yes, because when people say friction is always opposite to motion, well, no, it's not. It's opposite to the sliding surfaces. Oh, you've probably just seen a small picture of me, right? You didn't see the whole thing. But okay. I hope that was still useful. This is not true. Friction can cause motion. Motion. Okay. How fast can a car accelerate? Okay, so this is another example which I like. So you would think that a more powerful car would be able to accelerate faster. Okay, so when you have the ground, okay, this is my drawing of a car. It's a little hatchback. Okay, and this is the steering wheel. Right, so the wheels push the car forward. There's a friction between the wheels and the road, and that force is a forwards force because this most cars are front wheel drives. Front wheel drive, yeah, and there's a friction force here between the wheel and the road that pushes the car forward. Friction. Okay, but we know that the friction force is less than or equal to mu n. So the typical value, if we have coefficient of friction between coefficient of friction tire and road, 0.7 for dry roads and 0.4 for wet roads. I would say I would say it's a low estimate, but let's go with 0.7 for the dry road. So mu is 0.7 for a dry road. And so okay. Friction is mu n. Okay, so let's say the mass of the car is m. Let's say we don't know the mass of the car. And okay, so the only forwards force that is acting on the car is the Archie. Yes, the friction is not limited to one. It could be 2 or 3. Yeah. I was a firm believer that it couldn't, but actually I've convinced myself that you can have materials with coefficient of friction of more than 1. When the coefficient of friction is more than 1, no, it just means that the friction force is bigger than the weight of the car. That's it. That's all what it means. The friction force can exceed the weight of the car. It means you can accelerate faster than g. Literally, that's what it means. Okay, so the forward force. So we have Newton's second law. Newton's second law. That mass times acceleration is equal to the resultant force. But the resultant force is friction. That's the only force. The only force that it was, you ignore air resistance. The only forward force is friction. So mass times acceleration is the friction force, which is less than or equal to mu n. And mu n is mg, because you have mg and you have the normal reaction force. So mass acceleration is less than mu mg. And now, haha, I have to correct myself. I have to correct myself. But this would be true for a 4-wheel drive car. But we cannot do this. We're not allowed to do this. We have to say n and n. We have 2 different n's. We have n1 and n2. Because there's front and back wheels. For simplicity, let's assume n1, because the back wheel does not contribute to accelerating the car forward. The car is front wheel drive. Therefore, it's mu n1, so it's mu mg over 2. Mu mg over 2. Right, m cancels out, so acceleration of the car is less than or equal to mu g over 2. As you can see, it does not depend on the mass of the car. And it doesn't, okay, mu mg. And there's no power of the motor here. So mu is 0.7 times g, which is 10 for simplicity, 2, which is 3.5 meters per second squared. Now, how long will it take to accelerate? How long will it take to accelerate to? That means 0 to 60 miles an hour. So acceleration is final velocity. So 60 minus, so v minus u over t. 60 miles per hour. So time is v minus u divided by t. Let's say, so 60 miles an hour. So that's 60, that's 96 kilometers, 96 divided by 3.6. That's 27 meters a second. So 27 meters per second minus 0 divided by, so that's A, divided by 3.5. 27 divided by 3.5. So it should be about 7.7 seconds. So a typical car should do about, a typical front wheel drive car should do about 7.7 seconds from 0 to 60. A front wheel drive car, yeah. 7.7 seconds, and that's what Golf, if I only knew how to spell Volkswagen. Volkswagen Golf 0 to 60. Not to 60, between 6.5 and 10.1 seconds. Okay, which is very reasonable. Some cars go faster than this, 5.4 to 6.2. Now, there are problems with that. Like 4.5 seconds, for example. 4.5 seconds. The problem with that is now you are not limited by the power of the engine. The power of the engine doesn't play that much of a role. The most important part is the friction between the roads. So when somebody says the car goes from 0 to 60 in 3 seconds, you have to say, oh, what's the friction coefficient? Because if the friction is not enough, the wheels will spin, but the car will not accelerate as fast as you want it to. No, okay. Mass cancel is less than or equal to. That means that this is the ultimate acceleration that you cannot exceed. Of course, if you don't have a powerful engine enough to accelerate you at that rate, then of course, yeah, we're not talking about the same engine pulling the same. I'm saying that no matter how powerful your engine is, you will never be able to exceed the acceleration, because your acceleration is limited by the contact with the road. I divided by 2 because the weight is distributed evenly between the front and back wheels. We assume that it is distributed equally. It doesn't mean that necessarily true. It's not necessarily true. So a car cannot exceed the maximum acceleration because this is determined by the friction with the road. Maximum acceleration. So conclusion. What I'm trying to say. Conclusion. Acceleration of the car is limited by the friction with the road. Acceleration is limited by the friction with the road. Yeah. So a 4-wheel drive car will be able to accelerate twice as fast, so about 7 meters per second squared, because all wheels are included. This is so A max is about 3, well, it's mu mg, is mu g over 2 for a front wheel, so a 2-wheel drive, and A max is mu g for a 4-wheel drive car. 4-wheel drive car. Because that's, you're accelerating by the friction force, and the friction force cannot exceed cannot exceed mu mg. Is limited by the friction with the road. So yeah. So when you see somebody saying that the car accelerates from 0 to 60 in less than 2.7 seconds, for example, that means it accelerates faster than it will fall. Okay, if time 0 to 60 miles per hour is less than 2.7 seconds, that means you accelerate faster than free fall. Acceleration is faster than free fall. This is only possible. This is only possible. Only possible if mu is greater than 1. That means ideal conditions. It has to be an ideal road, ideal tires. So many things have to go perfect. Typically, what you'll have a wheel spin. Yeah, the wheels will spin, but the car wouldn't accelerate as fast. I hope that makes sense. I've spoken about this a lot in the previous webinar, so please watch last year's webinars on Newton's laws if you're still confused. So yeah. Okay, problem 4. A 60-kilogram child and a 30-kilogram child are going down a slide. Which child would go faster? Make all necessary assumptions. This is another question that 2.7 is for mu equals 1. For a four-wheel drive car with mu equals 1. Wheel drive with mu equals 1. There's another factor when the car accelerates, the distribution of the mass is different on the front and back wheels. So there's more force on the back wheels when it is accelerating, and also there's the downforce from the aerodynamics of the car, which pushes the car into the ground further. So there's a lot of stuff going on in there, but yeah, engineers have developed yeah, the 2.7 is for a four-wheel drive car with mu equals 1. But finally, yes, this is the ultimate. This is the ultimate maximum acceleration. Okay. Yeah. So two children going down a slide. Okay. So let's see. This is a child. A child of mass m. And there's the gravitational force, mg, and the incline is theta, and this is mg, and this is the normal reaction force. Now I'm going to split the mg into two components. I'm going to split mg into a component perpendicular to the slope and along the slope. So I've probably shown you this before. I have the x-axis along the slope. This is my x-axis, and my y-axis is perpendicular to the slope. So Newton's second law. Along the x-axis, I have mg, so this is mg cos theta, because this is theta, this angle is theta, and this is mg sine theta. So along the x-axis, mass times acceleration in the x direction is equal to mg sine theta. And for the y-axis, mass times acceleration in the y direction is equal to the forces upwards minus forces downwards. So n minus mg cos theta. And the acceleration in the y direction is 0, because it is 0. Oh yes, there is friction, of course. There is a friction force. And because they are going down a slide, we can safely say that the friction force is mu n. Sorry, mu mg sine theta minus mu n. Okay. So yeah, thank you. Sorry. So the forces, so the child is accelerating down the slope with acceleration a, and mass times acceleration is equal to mg sine ax. Mg sine theta minus mu n. No, okay, let's remove the x. So this is just like this. And this may is 0. Okay. Now, from here, I can immediately say that n is equal to mg cos theta. Okay. And I'm going to stick that into the first one. Okay, so mass acceleration is equal to mg sine theta minus mu mg cos theta. Because we're not moving along the y-axis. The y-axis is perpendicular to the slope. We're not moving along that axis. We're only moving along the x-axis. Okay. M cancels. And you can see that the acceleration of the child is equal to g, open bracket, sine theta minus mu cos theta. So, does the acceleration of the child depend on the mass of the child? No. What does it depend on? We're assuming the same slope. Of course, it depends on the angle, but whether they're going down the same slope. What's going to be different? Mu. I love the way you spelled mu. Yes, it's usually spelled mu. Yes. Oh wow. Somebody actually did you. Mu. So what does it depend on? How do you go faster on a slide? What do you need to do? Rougher or smoother? Yeah. Smoother clothes to make mu smaller. Absolutely. Reduce mu. That's the only way to go down a slide faster. It does not depend. Like I did experiments on a water slide. I was when I was roughly your age, probably. I thought about this, and I thought, well, who goes faster down the water slide? Do heavy people have an advantage? And no, they don't. It's only the way you position yourself and what you're wearing. That's the only two factors that affect how fast you go down a slide. Pour water down the slide, yes. Well, that's what happens in a water slide. I got I got very excited on a water slide once, and I still got a scar on my forehead. It's like a Harry Potter scar. So yeah, do experiments with water slides, but do them carefully, please. It was a bloodbath. Okay, so acceleration does not depend, only depends does not depend on mass. Depends on G, which planet you're in, of course, but on theta. Okay, now we assumed that, well, air resistance. How fast are you going? How fast are you going? Typically, at human speeds, air resistance isn't that fast. So I'd say it doesn't have too much effect. And yeah. One more thing I wanted to talk about is an experiment. So problem 5. A simple experiment to determine mu. Simple experiment. Simple experiment. Meant to determine mu. So mu depends on, let's have a look. Coefficient of friction for different surfaces. So these are typical values, but there's an easy experiment that you can do. So if you have an incline and you have a box on an incline, you have the friction force. Oh, sorry, the gravitational force. You have the friction force, and you have the normal reaction force. And just like before, this angle is theta. So we split this into components. So this is theta. This is mg. This is n. This is mu n. And this is mg sine theta and mg cos theta. Now the box will start moving, will start sliding. Box starts sliding when mg sine theta is equal to mu n. Because, well, technically this is the friction force. This is force of friction. And force of friction is less than or equal to mu n. So when the friction force reaches mu n, then it starts sliding. Okay. And we know that n is mg cos theta. So mg sine theta is equal to mu mg cos theta. So m cancels, g cancels, And we have mu is equal to sine theta divided by cos theta, which is tan theta. So basically, this is a very important criterion. Tan theta is greater than mu, slides down, with acceleration. So tan theta equal to mu, sliding down, or at the point of sliding, So just about to start sliding. And if tangent theta is less than mu, does not slide down. Down. Okay, so can somebody help me and tell me what experiment I can do to determine the friction force, let's say between all right, this calculator and this thingy-magic. Can somebody think of, take the slide and the box, move it up and down to change theta. Find the angle at which it starts sliding. Absolutely. Find the angle at which it starts sliding and measure that angle. And tangent of that angle is mu. Okay. So how to find method? Increase theta until it starts sliding. To measure tangent theta is mu. That's it. It's just very simple. As I said, it's a simple experiment. So let's do a experiment. So okay. This is a calculator and there's rubber bits here. Rubber on a book. So I move the book. Starts sliding. Up. So I've introduced a lot of uncertainty in my experiment, but hopefully I'm going to share my screen again. You see my screen? Okay. And blimey, I've been talking about friction for an hour and 20 minutes. Okay, so this is the angle. I've kept the book, so the calculator has moved, but I think I managed to keep the book at the same angle, at least this edge of the book at the same angle. And let's see if I can measure the angle. Well, I don't need to. I didn't need to measure the angle. I mean, need the tangent of that angle, right? So that's going to be what? So I'm going to take a ruler. I'm going to measure this on my screen. So on your screen, it could be different. This is 9.5 centimeters. 9.5 centimeters. And this is, oh, 9.5 centimeters. Wow. 5 centimeters. Was it really 45 degrees? It's a bit hard to believe. I thought it was more like 70. Oh yeah, it was about 45 degrees. Okay, so tangent, tangent, so tangent theta is equal to 1, so theta is 45 degrees. Yeah, moves 1. Moves 1 for rubber against my book. Okay, so yeah, simple example, simple experiment. And this is how I convinced myself that you can actually have coefficient of friction more than 1 with some materials. Okay, so problem 5. Problem 5. We have a smooth floor and 2 blocks on top. There's friction between the blocks, but there's no friction between the bottom block and the floor. The coefficient of friction between the blocks is 0.4. Find the acceleration of the blocks if force is 30 newtons and the force is 200 newtons. Okay, so to apply Newton's laws, we have to draw them separately. So we first draw the top block. Top block we draw separately, and we draw the forces acting on it. So M1G, N1, yeah, there's friction, there's normal reaction force. There's a force here, which is pushing the box, F, and there's a friction force down here. So the friction force, F, let's call it F1, why not? Okay, so what can we get from this? So mass, well, I mean, N1 is equal to M1G. I hope that's clear, because that's the vertical forces. The vertical forces are balanced because it's not moving up or down. Now we have the forward force. So mass acceleration, M1A, is equal to the force minus F1, which is the friction force. Okay, so when we write this, you analyze what are the things that we know and what are the things that we do not know. So I'm going to circle the things that are unknown. So N1 is unknown. And here F1 is unknown and A is unknown. So we have 3 unknowns in 2 equations. That's not good. We cannot solve it because we have more unknowns than equations. Okay, so we take the second box. Now I just have to mention is A1. We don't know whether the boxes have the same acceleration or not. We take for the second box, we have m2g. That's the weight pulling it down. There's a normal reaction force pushing it up, N2. And there's another force pushing it down, which is N1, because it's the top box pushing the bottom box down. There's no friction force on the bottom, but there is friction force on the top. And this time round, it's the Newton's third law pair of that force. So according to Newton's third law, this force has to be equal and opposite to that force. So this is going to be F1. This is the force. This is the opposite force. And that's it. That's the only force, F1. Okay. So we can write that N2 is equal to N1 plus M2G. Kind of useless information for us because we're not looking for N1 or N2. M2A2 is equal to F1. Okay. Now we also have to keep in mind that we have a limit. We have a limit F1. F1 is limited. F1 has to be less than or equal to mu N1, which is 0.4 multiplied by 0.4 multiplied by the boxes are 30 kilograms and 30 and 60 kilograms. Okay, times 30 times 10, which is 120 newtons. Though the maximum friction force is 120 newtons. Yeah. Actual maximum friction force. We just keep that in mind. So we solve. So we as I said, we don't really need this. We don't really need this. We solve these two equations. We solve these two equations, and okay. So we plug that in to here. So M1A1 equals to F minus M2A2. So M1A1 plus M2A2 is equal to F. Okay, so we want to find the acceleration of both boxes, but we need to assume that they're not they're not sliding past one another. And with a smaller force, it looks like it's not. I mean, the force with which you're pushing is 30 newtons. There's no way the friction force can be F2 and M2. Well, no, you can't. F1, because you don't know F1. F1 is limited by 120 newtons. It's up to 120 newtons. So we don't know F1, but we know that it cannot exceed 120. Now, here, there's not enough information. You have three unknowns. Sorry, you have two unknowns, but only one equation. But if the blocks are not sliding, if blocks are not sliding, then A1 is equal to A2. And let's call it A. So M1A plus M2A is F. So acceleration is F divided by M1 plus M2. It's kind of a was very easy to figure that out. Well, of course, if the boxes are not sliding, then F equals MA, right? So if 1A, if boxes are not sliding, then of course, then you have F equals MA. So F equals M1 plus M2A. That means acceleration sliding past one another. Then acceleration is F divided by M1 plus M2, which is 30 newtons divided by 30 plus 60 equals 30 divided by 90, 0.33 meters per second squared. So both boxes accelerate with 0.33. Now B, if we apply the same principle here, acceleration is F, which is, what was F? 200 newtons divided by 30 plus 60 is equal to, oh, okay, sorry, I'm doing the wrong way around. No, sorry, once again. Acceleration of the box. If the boxes are not sliding, if boxes are not sliding, then 200 divided by 90, which is 2.1, I think it's 2.1, so 200 divided by 90, 2.2, 2.2 meters per second squared. But if we look at this box, F1 cannot exceed. We know that this is less than 120 newtons, and therefore acceleration 2 is less than 120 newtons divided by M2, which is 60, which is 2 meters per second squared. So acceleration 2, the acceleration of the bottom box, cannot exceed, but acceleration 2 cannot exceed 2 meters per second squared. There's a limit, because you're limited, just like with the car, you're limited by the friction force. And therefore, the boxes are not sliding. So, boxes are sliding. So, boxes are sliding. And for the bottom box, F1 is 120 newtons. So acceleration 2 is 2 meters per second squared. Because that's the only force. The boxes are sliding past one another. And for the top box, well, we can use this. The top box, use this formula. Oh, no, sorry, not this one. This one. So I'm going to use a different color. So M1A1 plus M2A2 equal to F. Therefore, we have A1 is equal to F minus M2A2 divided by M1, which is F, which is 200 minus M2 60 times 2 divided by M1, which is 30. which is 80 over 30. 80 over 30, that's 2.7 meters per second squared. All right, so if you push slowly, both blocks move together. But if you push really hard, the bottom block moves as much as it can. It's limited by the friction force between the blocks. And the top blocks moves faster. So basically this slide past one another. I hope that makes sense. I have to finish here. So thank you. Yes, thank you for your attention. Raghav, what does it mean 60? Okay, if a car does 0 to 60 in 1.9 seconds, that means that it accelerates faster than G. And they base this calculation, the car manufacturers base this calculation on ideal conditions. So a car, no matter how good the car is, if you put it on a typical British road, it will never do 1.9 seconds. 4 seconds at, well, okay, 3.5 seconds at best. Okay, maybe 3. But 1.9 seconds, probably not. It's just, I mean, this must be a racetrack with, is a brand new racetrack. The tires have to be warm. I don't know. There needs to be wind in the same direction. There's just so many things have to be ideal for this to happen, but not on a, doesn't do it on a country road. Okay, you're welcome. All right, see you all.